Can you see my screen?
Yes.
Yeah.
Okay, so let me briefly remind you what we did at the previous lecture. So at the previous lecture, we introduced the photonic crystals. And photonic crystal is a periodic, at least in one dimension, structure with the period comparable with the wavelength. But talking about periodicity, I mean the periodicity of the electric function, because the electric function is a kind of potential for light, for as well. Electronic potential is potential for electrons or any charged particles. Yeah. So if the structure is periodic in 3 directions, like here, this is like 3D photonic crystal. If it's periodic in 2 dimensions, 2 directions, and we have, for example, just one and translation symmetry in one direction, is called 2D photonic crystal. But also, let me introduce another term. I didn't talk about it in the previous lecture. So let me consider that we have, for example, like 2D photonic crystal. Yeah, 2D photonic crystal. But of course, this thickness is finite. Yeah, finite. So in this case, we can say like 2D photonic crystal slab. So it's like a slab, but it's perforated, or it consists of some 2D array of particles. So in this case, we can say like a 2D slab of 2D photonic crystal. Yeah. Or if it's very thin, we also can say like a meta surface. So yeah, but usually if you talk about meta surface, we imply that the wavelength is bigger than the period of the structure. If it's comparable, it's just like a 2D photonic crystal slab. If it's a period is less than the wavelength, in this case, we can say this is like meta surface. Okay. So in this case, and for 1D photonic crystal, we also can say this is just a multilayer structure, okay, or Bragg structure. Okay. So this is some examples of photonic crystals. Yeah. Also, this is an example of photonic crystal fabricated in our lab. And then we introduced the transfer matrix method. Let me remind you that the transfer matrix method set the relation between the tangential component of electric and magnetic field at one interface and another interface. Yeah, we have some relation. So this relation is linear, so we can describe this dependence by some matrix. So here we can see this is a t-matrix or transfer matrix. This is a tangential component of electric and magnetic field at this interface. And this is a tangential component at the initial interface, yeah? So in principle, we could set H as arbitrary value. So for example, inside this slab. In this case, we can get the tangential component of electric and magnetic field in any position. Sorry? I'm sorry? I'm sorry? Could you repeat, please?
I think just someone forget to turn off his microphone.
Okay. So, and a couple of properties of transfer matrix method. So this is a property of multiplicity, yeah. So it's multiplicable. If you need to calculate the transfer matrix of multilayer structure, you need just to multiply transfer matrices for each layer, yeah. And determinant of the transfer matrix is equal to 1, yeah. Okay, so so, and then we apply the transfer matrix method for multilayer structure. So, and again, let me remind you that in a periodic structure, yeah, like here, solution is not periodic. Let me maybe just show you Bloch solution, yeah, Bloch wave function. And let's have a look at some figures. Yeah, like here. So for example, this one. So here you see that here we have some envelope function. Yeah, envelope function in some oscillations inside this envelope. Or like here, yes, you have also like envelope function. Yeah, and this envelope function, this is an exponential function. Yeah. And here inside this envelope, we have a periodic function. So this function is periodic. So if you, let's imagine that we have the envelope function is a constant. If envelope function is a constant, your solution will be periodic. Yeah. Yeah. So this is our, like, this is periodic function. Okay. So in addition to this, we have a translation symmetry along x and y directions. This is why here I can try to find the solution in the form of a plane wave along x and y axis. Yeah. Okay. So then we know that according to the Bloch theorem, if you add the period, yeah, here to that variable along the periodic direction. So in this case, solution, it's not periodic, yeah, but it's it has some relation with the initial function, yeah, e of y, x, and z, yeah, here. And this is, it gives just additional factor, this one. So this is from other hand, but from one hand, but on other hand, we know that the relation between the tangential component of the electric and magnetic field at this interface and this interface, so at other sides of the period, could be described by the transfer matrix method or using the Bloch theorem, this following relation. And here we clearly see that this exponential factor, yeah, this exponential factor is an eigenvalue of this matrix, yeah. And then we can write this in this form, and then we calculated the dispersion relation for TM and TE waves, yeah, dispersion relation. Yeah, the difference that between TM and TE, so you know the difference is polarization, but technically, so we need to use different transfer matrix methods, different transfer matrices, yeah, because for TE and TM, the transfer matrices are different, yeah. Okay, this is very beautiful and very simple technique, and actually, in these formulas were first obtained by Rytov in 1956. So, in this paper was published in JET Journal of Experimental and Technical Physics. Yeah, experimental and theoretical physics. Okay. So, and then we plot the solution. So, just for normal incidence, when there is no difference between TE and TM waves. Yeah. So, and at the left side, we see cosine function. It means that cosine cannot be bigger than 1 or less than -1. So, but this function can be more than 1. Yes, we see that it can be more than 1. So in this case, when this function is more than 1, this cosine, yeah, this cosine, its argument is pure imaginary, yeah. So in this case, Bloch wave number is imaginary. So in here, I plot the dispersion. So the dependence of frequency omega, yeah, omega, or K naught, yeah, here, because K naught is omega over C, yeah, on the Bloch wave number in the first Brillouin zone. And we see that we have many zones, many bands, allowed bands, yeah. So, and between these bands, we have a band gap. This band gap, and inside the band gap, the Bloch wave number is imaginary, and its absolute value is maximal in the center of the band gap. Okay, so a couple of remarks. Yeah. So here we plot the dispersion only for the normal incidence. Yeah. So when kx and ky are 0. Yeah. But of course, the position of band gap and the width of the band gap depends on the angle of incidence. And if you have an oblique incidence, it also depends on polarization. And let me ask you, is it possible to have the complete band gap? Saying complete band gap, I mean that the band gap will be at some frequencies at any angle of incidence and for both polarizations. What do you think? Is it possible to have a complete band gap for all polarizations and all angle of incidence at some frequency?
If we can change only angle of incidence, right?
So here let's imagine that we have some fixed design, so some fixed period, some certain refractive indices, yeah, and thickness of layers, yeah. And could we observe the band gap at some frequency for all angle of incidence and for both polarizations? So, because let me show you. Do you remember this this plot? Yeah, this is the band gap, and this is a dependence of reflectance. Yeah, reflectance on the frequency. So in here you see that the reflectance is 1 exactly in the region of the band gap. Yeah, but let me reformulate my question. Could we have the unit reflectance for any angle of incidence and for both polarizations?
No.
So the question is a little bit tricky. So
well, maybe that depends on which material do we use. Like if we got two, so we're talking about the electric.
yes,
material.
yes.
Oh, all right.
So, for metals, this is possible. This is possible.
Yeah. For metals, this is possible, definitely.
So, but yeah, you could take the very thick layer of metal. So in this case, yeah, we can have the complete band gap for metals. Yeah, because just a metal, yeah, it's. But for dielectrics, if the dielectrics are isotropic, so no uniaxial crystals, no biaxial crystal, just isotropic. So in this case, this is impossible. Yeah, you can have the band gap for some angle of incidence and maybe even for both polarizations, but you could find maybe some angle of incidence where you will have some transmittance through a structure. So, but complete band gap is possible to realize the complete gap even for dielectric materials for 3D photonic crystal. It's possible. For 3D photonic crystal, it is possible, yeah. And for 1D photonic crystal, it is possible only in the case of anisotropic materials. Moreover, you need to rotate the optical axis somehow with respect to the normal of your crystal. normal or direction for your interfaces. So it's a little bit tricky, but it is possible. Okay. Band gap, reflectance. So this is again reflectance. And we finish the lecture with this formula. It's about how to calculate the reflectance from the periodic structure of finite thickness. Yeah. The main idea that the field at the left side is consist of the incident field with unit amplitude and reflected field. Yeah. And here, so in this case, the total electric field is 1 plus R, and total magnetic field is 1 minus R. Yeah, and this is a transmitted amplitudes of the transmitted electric and magnetic field. Yeah, okay. This is a finite formula. So this is some examples. So here we see how the reflectance depends on the number of layers. So if you increase the number of layers, we see this so-called Ewald table. Yeah, this one. Yeah. Okay. So, okay, and now we will consider so-called the effective medium approximation. So we will consider the case when the wavelength is much bigger than the period of my structure. Okay? So wavelength is much bigger. So this is not photonic crystal in this regime. This is like metamaterial. And we see that here, yeah, when we have very low frequency, large wavelength, dispersion of our photonic crystal is linear. Yeah, so it means that we could describe the dispersion just by one number, effective refractive index or effective permittivity. And let me directly calculate this effective permittivity or effective refractive index as a function of period, of thickness of my layers, and permittivity of my layers. Okay, let's start. And I think I will start with this formula. Yeah, with this formula. N1 D1 keynote. So I will consider. So this is a normal incidence. This is a. I think it's not applicable here. So here it's N1 D1 keynote, but in general case, I should write here. What should I write here in the general case, guys? Instead, N1 D1 keynote.
At an angle?
No. Here, instead N1 D1 keynote, we should write just K1 D1. Maybe let me open the. Let's take it. Yeah. Okay. N1. Oh, I'm sorry. K1 D1. This is I should write in general case. Where? Yeah. And what is K1? K1 square. You remember? It just. This is a. What is K1? What is the physical meaning of K1? K1 is just a Z component of wave number inside the layer 1. Yeah. It's just a wave number in the material with epsilon 1. Yeah, with permittivity epsilon 1. So okay, what is equal to K1 square?
K naught squared minus K.
Var epsilon 1, because it's in the first layer, yeah, with a permittivity epsilon 1. Okay, K naught square. Yeah, this is true. Minus, in the general case, kx square minus ky square. Yeah. So, and here we see that this is the same. I will just would like to rewrite this expression in the following form. That, sorry. That epsilon 1 k naught square is just kx square plus ky square plus kz square, but kz is k1 in our case. Okay, and here we can write the expression for k1. The same story for k2. Yeah, of course I need just to replace epsilon 1 to epsilon 2 and k1 to k2. Yeah, completely the same story. This is in each layer. Okay, so next step, actually we should take this expression, yeah, for TE waves and for TM waves, and consider the limit of effective medium. So what does it mean? So here, if the wavelength is huge, yeah, we need to put KBD, yeah. We should assume that KBD is much less than 1, yeah. Okay, and at the same time K1 D1 is also much less than 1. Is there any mistake here? Okay. K1 D1, yeah. So, and K2 D2, yeah. This is our assumption, yeah. So in this case, if K1 D1 much less than 1 and K2 D2 much less than 1, in this case we could expand the cosine and this cosine and this sine and this sine into the series, yeah. Just a reminder for you, yeah. What is the approximation for sine function? Sine z, what is equal to approximately?
Z.
Yes, z, and next term. So actually, we don't need next term here, yeah. But next term is z cube, yeah. Z cube over 3 factorial, yeah. This is for sine function. And what about cosine function? Cosine z?
1 minus z squared over 2 factorial.
Yes, exactly. Yeah, it's z square over 2 factorial. Yeah, z square over 2 factorial. Yeah. Okay, this is true. So, but I think so. Of course, we need to have expansion here, expansion here, expansion here, expansion here. But maybe it will be much easier to consider this formula. Yeah. Do you remember? This is the formula that we have, but here I need to write not n1 d1 k naught. Here I need to write just k1 d1, k2 d2, yeah, and alpha. Alpha. This is a factor alpha, yeah. Okay, and we can rewrite the right part of this equation, yeah, in the following form. So this is our, okay, we need to put it to the left side, yeah. Okay, we can expand cosine, and then expand this cosine and this cosine. I think it will be easier, yeah. Let's try to do this, guys. So let's try to rewrite this expression in the limit when KBD much less than 1, K1 D1, and K2 D2 also much less than 1. Okay, let's try to expand this. So this is a quite technical part, but it is very useful. The final expression will be very beautiful and quite short. Okay, okay, let's try. So first, okay, I will divide it by 2 and put the cosine to the left and divide both sides by -1. Okay, okay, cosine is 1 minus KBD over 2. Yeah. In principle, guys, if you like, I can just write it here, yeah, and then I will just copy this and send this to you, if you like.
Yes, please.
Okay, so it's not a problem for me. Yeah, it's 1 minus just fraction, yes, KBD. This is a square and 2. Yeah, this is the left part. Okay, and what about the right part? Here I should write like 1 plus alpha over 2 cosine. Yeah, cosine again. Okay, I will write it cosine again. What should I write here? Like 1 minus here K1 D1 plus K2 D2. Okay, do you agree?
Yeah.
Here. Okay, so this is a first bracket, yeah, and please remember what is alpha is 1 over 2, yeah, and 1. But in my case, alpha is not so simple, because let me go back and have a look what is alpha, yeah. Alpha in my case is so guys, let me consider maybe TM polarization, yeah, TM polarization, and this is alpha, yeah, in my case 1 over 2 and this expression. Okay, this is alpha. So this is let me go back. This is a first bracket, and here where is it? Sorry, here 1 minus alpha. Okay, the same fraction, yeah, but plus 1 minus alpha, and here I also should put minus, something like this. This is expression, yeah. Okay. Can I simplify this expression somehow? So I also need to write what is okay. Let me simplify it a little bit, and then I will substitute alpha. Yeah. For TM polarization, let me write what is alpha. alpha is 1 epsilon 1. K1. To K2. Okay, and fraction 1/2, yeah. And this is alpha, okay, but I will substitute it later. This is correct. What I see, guys, please have a look. Here we see 1 here. Here we have 1/2 multiplied by 1, and here 1/2 multiplied by 1. Is it clear for you that 1 is cancelled out?
Yes.
Okay, and so we can simplify this expression further. So I can write here, I don't need here 1, and also I think I don't need to write here minus. Okay, I will write minus. Next, 1/2, this bracket, and 1/, so, and maybe let me multiply both sides by 2. Don't you mind?
No, we don't.
Okay. So in this case, I don't need fraction anymore. Yeah. Here I have just this factor. So there is no 2. There is no 2. So I have sum of this bracket and this bracket. Yeah. This bracket plus this bracket with minus. Sorry. So this is correct, yeah. So, but I think maybe I skip 1/2 here, yeah. For both. Is it true? Yeah. One over 2, and here 1/2 too. Yeah. So, and what is it? And also, I need to write just. Please have a look. With alpha, yeah, with alpha. Alpha/2, but 2, there is no 2. What should I write here, guys?
You forgot alpha.
Yes. Okay, let's write plus alpha, and then.
Just a second.
Or minus alpha. Let's write maybe minus alpha. The same bracket, guys, like here, yeah. with minus, and here with plus. So this is a difference, should be difference, yes? Please have a look. Probably I lose minus, yeah?
Yeah.
I lost minus in the first here, yeah? Okay, maybe let me write left here, right here. And minus here, yeah? Check me please again.
That's correct.
That's correct. So it seems that I don't need minus here, here, and here. Let me write maybe plus, plus, and plus, yeah. I would like to highlight this is here, I have a plus. So plus, 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 okay. But I definitely can simplify this expression, yes? So the first term is okay. This term, let me have a look. This is okay. It seems that the cross term is cancelled out, and I can write here like in here k2d2 square, yeah, with factor 2. This is just the first bracket, guys. Please have a look. Because here I should the same terms, yeah, factor 2. I think I don't need this factor 2, yeah, just like here. Is it correct about the first term?
Yeah.
Yes. Yes.
So, and here in this case I have just a double cross term, yeah. So it means inside this bracket I should write like a factor 4, yeah. Something like this. Of course I don't need this left and right. Do you agree?
Yes.
So it's like just 2 alpha, yeah, just 2 alpha, just 2 alpha. Okay, guys. 2 alpha, okay, almost. And now I would like to write the dispersion, yeah, the dispersion. So I know what is k1 square, but let me write, guys, maybe about k1 square or k2 square. Kz is it's k1, yeah, it's the component of the wave number perpendicular to the interfaces, and kx and ky, it's a components parallel to the layers, yeah, to the interfaces. And I would like to write this component in the following form, like here, just minus k parallel, and here also k parallel, like here. Please have a look. you see that K1 is epsilon1 K naught square minus K parallel. Parallel means parallel to the layers. Okay?
Yes.
Okay. So, and I need to substitute this. What is K1, D1, and so on and so forth. Let me do this. Okay.
May I ask you?
Yes, sure.
Will we have something like dispersion equation for anisotropic media after all?
Yes, exactly.
Does it look like? All right.
It's almost, yeah, but I would like to write this expression exactly in the form of dispersion for the extraordinary wave. And then when we compare the final expression with the known expression for the dispersion of extraordinary wave in uniaxial crystal, we definitely can find the expression for effective permittivity. Okay. So K1, D1, and here I also have alpha. Let me check. Do I really need K1, D1? Okay, guys. Let me first. I would like to have a look at alpha here. It seems that I don't need this term to alpha. I'm not sure. Let me check it. Let's. Okay, guys. Let me calculate to alpha K1 D1, but maybe I need. So here it's much less than 1 square, minus this 1 here, and this is so okay. Maybe I need this K1 square. I need just to substitute this one, yeah. Let me do this. It's just D1 square, and here I should write epsilon 1, yes, K naught square minus K parallel square. And here plus D2 square, epsilon 2, and also K parallel. Okay. And here plus 2 alpha. Let me consider maybe a sum. Yeah, alpha is 1/2 fraction, and here y epsilon square K1 square plus the same story for two square, and here in the denominator I should write y epsilon, and here 2 and 2. Please have a look. Is it correct? And but I have it's not factor 2, so I don't need here 1/2. Yeah.
And there's
And additional terms. Yeah. And because k1 d1 here in denominator, I don't need to write them. Yeah. I need to write just a d1 d2. Yeah. d1 d2. Yeah. Okay, guys, is it correct?
Yes.
Okay. And now let me collect all the terms with k node at the left, okay, at the right part of my equation, and all other terms at the left part. And I also need, I would just a moment. I also need to expand this k1 square and k2 square, yeah? Let's do this. So the same expression, but here, what should I write? Epsilon 1 over epsilon 2. And k1, this is expression for k1 square, yeah? And this is expression for k2 square. Do you agree?
Yeah.
So, okay. And now let's try to rewrite and collect all the terms with k node, yeah, at the left part of my, or at the right part of my equation. Okay, let me do this with a piece of paper first. Or maybe I will just directly write what I will have k node square left, right. One square. Epsilon 1. Epsilon 2d2. This is okay. This is from these terms. Okay, and then from these terms. So this is a little bit more complicated. What should I write here? Epsilon 1 square. Yeah. Epsilon 1 square over epsilon 2 over epsilon 2 d1 d2. Yeah. Here epsilon 2 square over epsilon 1. Mm-hmm. Do you agree, guys?
Yes.
This is a like just a term before k naught square. Okay, and this should be equal to, let me write, kb this one, and here I have minus k parallel and minus k parallel square, and here left. So, and let me collect all the terms before k parallel, yeah? Here is minus, 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 but I will put all to the left part, okay? Okay, here just d1 square, yeah? d1 square plus d2 square. And here, epsilon 1, epsilon 2, so it's just a ratio plus fraction. Epsilon 1 over epsilon 2, and here d1, d2, and plus very similar expression, d2 over d1. And k parallel with a plus, yeah. Guys?
Yes.
This is the final answer. So, but it seems that it looks very strange, yes? It looks quite strange. And actually, this expression could be simplified. Could be simplified. Let me do this. Let's have a look at the first bracket here. The first bracket, this one. And let me try to combine first term and third term. The first term and third term, they have common factor, yeah? Epsilon 1, d1. Do you agree?
Yes.
Okay, let's do this. So epsilon 1 d1 is a common factor. And what is inside the bracket?
d1 plus epsilon 1 over epsilon 2 d2.
Yes, d1 plus and ratio. And here d2, yeah. d2, and here ratio epsilon 1. Epsilon 1, and here epsilon 2, yeah? This is the first bracket, and
you didn't delete the third term.
yes. Let me work with there. It's just first part epsilon 1 d1 plus this one, and then I don't need these terms. I need to write just plus, and here epsilon 2 d2, yes, and here d2 plus d1 over d2 d1, yeah. Okay, Is it correct, guys?
Yes.
Yes. And what else? And it seems this is quite reasonable. I could write the expression inside these parents in a as a single fraction. You see? Let me rewrite this. So I just need to take a sum here. Yeah. Inside the bracket. What will I have? I will have just a single bracket. Yeah. And single fraction. What is a fraction? Epsilon 2.
Epsilon 2 d1 plus epsilon 1 d2.
Exactly. Epsilon 2 d or epsilon 1 d2 plus epsilon 2 d1 yeah, and very similar expression I can write for the second term. Yeah. Okay, and is it evident for you that we will have the same bracket, epsilon 1 d2 epsilon 2 d1, and here I will have epsilon 1 d2 epsilon 2 d1.
Yes.
So it means this is a common factor. Okay, maybe let me write this common factor here. It's epsilon 1 d2 plus epsilon 2 d1. Okay, and what I will have more epsilon 1 d1 epsilon 2, and here epsilon 2 d2 over epsilon 1. Yeah. Okay, I can write this. Just take a sum. Yeah.
Yes.
Okay, and let me do this. What will I have in this case? This is a common factor, epsilon 1 d2. Epsilon 1 squared d1, yeah? Epsilon 1 square d1. Yeah, epsilon 1 did, okay. And plus epsilon 2 square d2, and in the denominator I should write epsilon 1 epsilon 2. Okay, beautiful, beautiful. So guys, this is their expression in the left part. And what should I write at the right part? Here we see something similar, and let me write d1 is a common factor for the first and third term. Yeah. So I can write here plus k parallel square, yeah, and here inside the brackets I can write here d1 is a common factor, yeah, and here I can write d1 plus fraction like d2, and here epsilon 1 over epsilon 2, epsilon 1 over square left d1. This is okay. Here, okay. I cannot see the mistake in the expression. Not sure. Oh, okay, I found. And very similar story for the second bracket. D1, D2, D1, D2, D1. Okay. Okay, guys, and here I can also write the same bracket here I will have, you see? I can write this as a single fraction, yeah? And I will have epsilon 1 d1 plus epsilon 1 d2 plus epsilon 2 d1, yeah? K parallel square. And here, d1, let me write this in the following form. Like d1 over epsilon 2 plus d2 over epsilon 1. And this is a left, right, and the fraction the same as in the left part. Var epsilon 1 d2 epsilon 2 d1. Check me, please, guys. Sorry?
That's correct.
That's correct, yeah. And I think I have a maybe small mistake here. Let me check. And at the left part, guys, please have a look. Why I have square here? Is it true?
Yes.
Just a moment. Epsilon 2 d2, epsilon 1 d1 ratio. Maybe, guys, it's reasonable to write it in a little bit different form. Just let me have a look. Oh no, it's okay. I can divide it, yeah? They have a common factor, yes? This one and this one, yeah?
Yes, I have.
Yes, okay. Okay, and let me divide both left and right part by this huge bracket. Okay?
Okay.
Let me do this. So in this case, in the left part, I have just k naught square. And here I have this fraction. Huge one. Yes, and here I will have k parallel. Yeah. K parallel fraction also I should write here. In denominator this expression and in numerator the previous one. Yeah. K square. And here we see that this term cancel out, yeah? Epsilon 1 d2, epsilon 2 d1 with this term, yeah?
Yes.
Okay. Let me do this. And let me a little bit simplify this expression also, yeah? It's d1.
We can multiply числитель знаменатель by epsilon 1, epsilon 2.
Exactly. I would like to do the same, yeah. I would like to do the same. But before epsilon, just a moment, give me a small pause, please. Yes. Epsilon 1 d1 plus epsilon 2 d2. And in denominator, I will have 1 square d1 plus epsilon 2 square d2. Just a moment. And what about here? d1 over epsilon 2. Epsilon 1. So it seems that I will have a small mistake somewhere. I'm not sure. Okay, let me here fraction. Fraction, I don't need this fraction. Yes, like this one, yes. And if I will multiply.
But why? No, we shouldn't have epsilon 1, epsilon 2 in the last denominator.
And in the numerator, we should have the same indexes, like epsilon 1 d1 plus epsilon 2
Here in
Yeah.
it's I see d1 over epsilon 2 it should be, yeah. Yes, I agree. So it's a fraction. Okay. I should write here d1 over epsilon 2, yeah. And here, and plus d2 over epsilon 1, yeah? Like here, yeah?
Yeah.
Okay. It's a little bit strange. I think I have a mistake somewhere, because here I should definitely have just d1 plus d2 instead this fraction. Let's have a look how I get this fraction. This one.
We have square of epsilon because we say that k1.
We start from this.
To...
We start from this, yeah.
So yes, and this
here
is
it's d2, yeah, and then we write epsilon 1 d1, d1 plus epsilon over d2, and then so it seems that this is correct, and let's go back a little bit.
Yes, the mistake should be earlier.
Let's have a look here. Here our keynote. I think this is correct. And what about here? Let me have a look at this expression. Yeah. Epsilon 1 square K1 square. It's epsilon 1 cube, epsilon 1 square over 2. And here, d1, d2. Go back.
Maybe we would have d1 plus d2 for T polarization. But for Tm, I think they should retain epsilons.
Where? Let's check. This expression is correct. Let's check it. It's just 1 minus cosine. That's 1 minus, okay. And this is, okay, this is cosine, this is a cosine, yeah? I think this is correct, yeah? Cosine, cosine, yeah? Here, 1 is cancel out, yeah? Have, okay, minus here, then minus 1 minus 1 over 2 plus this bracket. This bracket is correct. But what about this bracket? What about this bracket? Alpha and alpha plus alpha minus alpha plus. So, but it seems that also correct. Alpha over 2 here, yeah? It seems that this is correct. This is correct, and maybe the mistake in the alpha, no? No, it seems it's correct, yeah. Let me check the expression for alpha, but I think it's correct. Yeah. Epsilon 2 kz1, epsilon, yeah. Epsilon. Oh, guys, I see. Mistake is here in alpha. Oh, here, because in alpha I should write, sorry, epsilon 1 k2, epsilon 2 k1, epsilon 2 k1, epsilon 1 k2. Please have a look. You see the difference? Before I wrote epsilon 1 k1, epsilon.
Yes, we see it.
Okay, so so in this case, let me maybe briefly rewrite this. I think it will be quite easy to correct. What should I write here? Epsilon 1 square. Okay, 1 over 2. Yeah. Again, I'm sorry for this. Yeah. Epsilon 1 over 2, and here was an fraction. The same denominator, yeah. The same denominator. Epsilon 1, epsilon 2, k1, k2. But in nominator, I'll have epsilon 1, epsilon 2, yeah. No, epsilon 1 square. and K2 square. In 1 square. Mm-hmm. Is it correct? No.
I hope so.
Yes, guys. This is. I'm sorry. Okay, maybe let's make a small pause and then continue. This is a quite technical part. Yeah, it's quite cumbersome, but I think we will correct. Okay, let's start. Let's say in 17 minutes. Let's 10 to noon. Okay.
All right.
Okay, 10 to noon, guys. Mm-hmm. Okay, dear colleagues, let's start. So I'm sorry for this mistake, but I think we will correct it fast. Okay, the difference is here, yeah. So this is a new expression. The difference only in numerator, yeah. Here I should write epsilon 1 square K2 square. Okay. So, and here it's let me have a look at this expression. So here I wrote K1 T1. So in numerator I have still epsilon 1 epsilon 2, yeah. But here the difference, I should write here K2 instead K1 and here K1 instead K2. So it means that here epsilon 1 square is the same, but in this bracket I should write, let me write K2, where is this expression? Let me write, here is 1 minus, then with alpha, then with plus, I can here, yeah? And here I should write epsilon 1 K2, epsilon 2 K1. Let's have a look. Yeah, here, you see, epsilon 1. And now this is correct, yeah? So it means that next, I should write here epsilon 1 square, epsilon 2, and here epsilon 2, epsilon 1. This is the only difference. This is the only difference here. Okay. And then, guys, here, let me have a look. What I will have here. Here, epsilon 1 square, epsilon 2, epsilon 1, epsilon 2. Guys, can you hear me?
Yes.
Yes, yes, we can.
Because just Zoom notified me about the pure internet connection. Okay. So, and now the expression is much more easy because here you have epsilon 1 square, epsilon 2, here epsilon 1, epsilon 2. So I can cancel out epsilon 2 and epsilon 1 square also, yeah. I will have, what I will have here? Just epsilon 1, here, d1, d2. So it means that here I will have just epsilon 1 d1 d2, and here epsilon 2 d1 d2. So let me rewrite this second bracket. Like d1, and here just d2 epsilon 2. It's here, yeah. Let me have a look. It's here, yeah, and this one. And the same story in the last bracket, because you see also epsilon 1, epsilon 2, d1, d2. This term comes from this one. So here I also should write at the right part d1, d2, and here no fraction. Just epsilon 1. And here also no fraction, just epsilon 2. Okay? So, and I think now we can just rewrite the following expressions. So, and now it's much more easier, yeah, guys? I see here the common term. What is the common term for the first, common factor for the first and third term? Epsilon 1 d1, yeah?
Yes.
So, let me do this. So, epsilon 1 d1 and epsilon 1 d1 and I will have just d1 plus d2, yeah? And here epsilon 2 d2. But what is d1 plus d2? It's just d, it's full period, yeah, of my structure.
Yes.
Yeah, okay. And here also, I can do a very similar thing in the last bracket here. D1, yeah, it's a common factor here. Let me rewrite this. So here, it's like epsilon 1 d1 plus epsilon 2 d2. This is the left part, yeah? And right part will be also d1 is a common factor. I will have epsilon 1 d1. Yeah, epsilon 1 d1 and plus epsilon 2 d2. Yeah. And okay, let me write. D1 here plus D2 here. D1 epsilon 1 D2. Oh no, I'm sorry, it's not so obvious, yeah. Okay, d1 plus epsilon 1 d2 is d2 epsilon 2 d1 epsilon 2 d1. Or maybe it's reasonable to combine other terms. Please have a look. Maybe d. If I will combine.
Why don't you have a term with denominator epsilon 1, epsilon 2? They do not...
Oh.
Для k параллельного они не сокращаются.
Sorry? Okay, let me have a look. Just a moment. For k parallel, yeah, for k parallel, for k parallel, I have. Yes, I'm epsilon 1 over epsilon 2, yeah? d1, d2. Because for k parallel, I have epsilon 1 over epsilon 2 and d1, d2.
Yes, plus epsilon 2 over epsilon 1, d1, d2.
Okay, from here, okay, so here I should write a fraction, yeah? Sorry. Here I should write a fraction, yeah. It means that here
Actually, it should be the same equation, not equation, the same term for k parallel, because it doesn't change. Can you
no, I see.
It won't change.
Yes, I see, because there is no change here, yeah, because the change on in epsilon, yeah. I agree with you. Okay. Anyway, I should write here. It's like var epsilon 1 over fraction. Just a moment, because I didn't save it. Yeah. Fraction. Yes, I agree with you. I agree with you that it should be the same. Yeah. As in the previous case. And now, is it correct? Please have a look.
Yes.
Yes.
Thank you. So, and now I can write d1 is a common factor, yes. And could you maybe tell me the final expression? What should I write here in the second bracket?
Yes, just a second.
I can say, don't you mind?
Yes,
So
please. Yeah.
it should be in the first bracket. Epsilon 1 d2 plus epsilon 2 d1.
I'm sorry. Var epsilon 1 d2
Yes, plus epsilon 2 d1.
Okay, plus epsilon 2 d1. Yes.
Then another bracket is
Just a moment. Just a moment. Yes, and the second bracket.
d1 over epsilon 2.
Okay. Okay. This is
Plus
looks correct.
d2 over epsilon
D1,
1.
D1 over.
Epsilon 2.
Are you sure?
Yeah.
Yes, it's right.
Mm-hmm.
Plus
D2 over epsilon 1.
yeah.
Plus, yes, I forgot plus somewhere. Okay, please have a look. Is it correct now?
Yes, and we can multiply the second bracket for epsilon 1, epsilon 2, and then we will have the same bracket on the left side and in the right side, like epsilon 1 d1 plus epsilon 2 d2.
Okay, 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 I agree. That's okay. Let me write. So I need just to rewrite this last bracket here, yeah?
Yes.
So, and I prefer to write, okay, here I will write fraction, and here epsilon 1, epsilon 2. And here I can write just bracket epsilon 2 d2. Please have a look. Is it correct now?
Yes.
Yes.
So, okay, guys, many thanks. Many thanks. So, and now the final step. The final step is following. I need again divide all of this left and right part by these two brackets. Okay. Okay. Let me do this. So again, I will have just K node here. Yeah, this fraction. And here, okay. But again, it seems that, okay, okay, this is correct. And now in the first bracket, guys, I will divide numerator and denominator by d square. Okay?
Okay.
Okay. So again, I will have here means that just kb square. And here in numerator, I will have, in denominator, I will have fraction here. Fraction here. This is our the first term. Okay, and now these terms cancel out. Okay, this is also D here, and I would like to write this term in the following form. Just a moment. Okay, parallel. So fraction K parallel, and here diffraction d1 plus d2, and in denominator I will have another fraction d2 over epsilon 2. Please have a look. So where D1 and D2 is just a period, yeah? D1 and D2 just the thickness of layers. Okay? What we can see here, guys? Now we see that this expression is very similar to the case of uniaxial crystal. For p-polarized wave, usually for uniaxial crystal we can write. So in my case, KB is KZ, yeah. It's just KZ square, and here I should write var epsilon. So when my wave have only KZ component is ordinary, yeah, and here plus K parallel extraordinary. I'm sorry. Okay. This expression. So, and it means that now we have these constants. Yeah. So it means that in my case, now the epsilon ordinary is this expression. And epsilon extraordinary is this expression. Mm-hmm. Oh, but actually, I prefer to write it just in extraordinary, yeah, extraordinary. A little different form. For ordinary, it is okay, but actually, it's more beautiful to write the expression for the epsilon extraordinary as follows. Epsilon extraordinary like d1 epsilon 1 and here epsilon 2 d2. Okay, please have a look. You see, this is for extraordinary. Okay, but why we have these expressions for ordinary and extraordinary? What is the reason? So we see that it's real. So our structure, let me go to maybe to my presentation. So our structure really behaves as uniaxial isotropic crystal. So what is the optical axis direction? So optical axis is a z direction, yeah, z direction. So if my wave propagates only along z direction, let's have a look. If it propagates only along z direction, kx and ky are 0, yeah? And I have only this component. By this component, xx, this one, yeah? This one. This is ordinary, because if my wave propagates along z direction, electric field is directed parallel to the layers. And this means that it's like an ordinary polarization, yeah? And for a polarized wave, my electric field has two components. One component parallel to the layers and one perpendicular to the layers. So it has a component of electric field along the optical axis. Okay, guys, it's clear?
Yes.
So, but anyway, actually this expression, we can easily get this expression in a very simple way, very simple way. I can show you. But I think I can plot something here, yeah, guys? Let me do this. Could I annotate? Okay, I can annotate. Okay, draw. Let's imagine that I have a capacitor. Sorry. That I have a capacitor here and here. Okay. So, and now let's imagine that this capacitor, so here I have my metamaterial or my periodic structure. Here it's like epsilon 1, here it's epsilon 2, okay? And here I have like D1 and D2. And the total thickness of my capacitor is D. Yeah. So effective medium approximation is quite close. It's very similar to quasi-static approximation, because quasi-static approximation means that you have almost static field. It means that the wavelength is huge because frequency is very low. Okay. Okay. Let me ask you guys, can you calculate or can you find the capacitor, yeah, with the same surface area for claddings. So it's the surface area is the same. The thickness is the same, but it's homogeneous with some homogeneous dielectric.
We should use a formula for последовательность соединенных конденсаторов или емкости.
Exactly, exactly. And what are the equation for the, so could you write the expression for capacitance? If you know, let me go back maybe. Oh, okay, it's not coming. Okay. What the expression for the capacitance? What is equal to? If you know the
epsilon S over D, something like that.
Yes, but okay, we can work with Gaussian units or with their standard system of units.
Okay, in C it is epsilon 0 or epsilon S over D.
Okay, in standard system of units, let's write epsilon naught epsilon, yeah, then
S.
Sorry, raise. Okay, exactly. S over D, yeah. Okay. And here I have the two capacitance, yeah, two capacitors, because this scheme is equivalent, yeah, to the following. I'm sorry. Like two capacitors, yeah, with epsilon 1 and epsilon 2, yeah. Okay, and what is the expression for capacitance?
1 over C is equal to 1 over C1 plus 1 over C2.
Exactly. 1 over C is equal to 1 over C1, 1 over C2. 1 over C1, 1 over C2. Plus 1 over C2. Exactly. So, and now I can write it in the following form. Okay, I need to substitute. It will be D, because surface area is the same. It means that D over epsilon, yeah, this is unknown epsilon, effective epsilon, yeah, is equal to D1 over epsilon 1 plus epsilon 2 over D2 plus, I'm sorry, D2 over epsilon 2. I'm sorry, guys. Okay, guys. So, and you see that in this case, electric field, yeah, the direction of electric field is like here. So it's perpendicular to the layers. So like along optical axis of my structure, yeah. In principle, you could consider many layers, yeah. So not just 2 layers. If you could write that expression for 3 layers, In this case, will be like epsilon 3, d3 or over epsilon 3. Okay? So, and when the electric field is along the optical axis, propagation of direction of my wave is perpendicular to the optical axis. Okay? And this is, of course, extraordinary wave. So, and this is expression for extraordinary permittivity, extraordinary. Okay? Is it clear, guys?
Yes.
So, and now let me write, consider another situation. So I have capacitor, and this capacitor partly consists of epsilon 1. Sorry, I have some delay in drawing. Yeah. Epsilon 1, epsilon 2. So, and surface area is like S1 and like S2. But surface area is proportional to the length, yeah? I would say like D1 and D2. But now D1 and D2, so I just rotate my structure, yeah? Now this is D2, yeah? And this is D1. So it means that my multilayer structure, the layers of my structure are horizontal, yeah? Okay? And
Yes.
now I need to calculate I'll say the capacitance. I need to calculate the capacitance of the capacitor with some epsilon, yeah, some epsilon ordinary. But in this case, this is just two parallel capacitors, yeah. It means that C equal to just C1 plus C2, yeah. Do you agree? Yeah.
Yeah.
Yes.
So, and here, according to the formula, it's just total surface area, but it's proportional to d1 over d2. In this case, it's kind of height of my cladding layers, yeah. And here I should write epsilon effective or epsilon ordinary, yeah, divided by divided by thickness, but let's say the distance between, let's say this is kind of L, yeah. And for two of my capacitors, like here, for parallel one, it will be just epsilon 1 d1 over L, because this distance, this is L, yeah. It's the same as here. Plus epsilon 2 okay, one can see this is a the same, yeah. L is cancelled out, and epsilon ordinary is just epsilon 1 d1 plus epsilon 2 over the period. So this is exactly, so let me, can I clear everything?
Yes.
Okay. So, okay. This is like it means that this expression, this is just a quasi-static approximation. Yeah. And you can find these effective parameters like effective parameters of permittivity in terms of capacitance. Yeah, some effective capacitance. It's related to effective permittivity, and it depends on the orientation of your multilayer structure inside between the cladding layers of the capacitor. What is interesting, guys? The interesting story, for example, is when one layer is metal and one layer is dielectric. In this case, when one layer is metal and one layer is dielectric, it is possible to find some regimes when, for example, ordinary permittivity is positive, but extraordinary permittivity is negative. This is called like a metal dielectric structure, but this is metal dielectric structure is sub-wavelength. In this case, it's a very strong anisotropic uniaxial crystal. So for natural materials, anisotropy is very, very, very weak. It's extremely weak. So usually it's difficult to observe anisotropy, yeah. And in regular materials, it's really weak, yeah. But if you fabricate this artificial multilayer structure, like let's say metal dielectric structure, like a 10 nanometers of metal, like a 10 nanometers of glass, 10 and so on and so forth, yeah. This kind of metamaterial, because it's sub-wavelength, metal dielectric, and this is very strong, very anisotropic uniaxial crystal. That one permittivity is negative, one is positive. And do you know how I can call this material with different sign of ordinary and extraordinary permittivity? Any ideas? So it means that please have a look at this expression, yeah, guys. And let's say that this permittivity is positive and this permittivity is negative. What can you say about this material?
It's dielectric?
No, it's not a dielectric. It's like from one point of view, it's dielectric because one permittivity is positive. But from other point of view, it's like a metal.
Oh, okay, then it's supposed to be metamaterial.
It's a metamaterial, but this metamaterial has a specific name.
Perovskite?
No, not the perovskite. Perovskite, it's type of crystalline lattice. It's natural materials. There are a lot of perovskites in nature. This is called hyperbolic metamaterial. Have you ever heard about hyperbolic metamaterials?
Yes.
So, but why it is called hyperbolic?
Because it looks like an equation of hyperbolic.
Exactly. So, guys, I can consider. So I can try to plot, for example. I can fix the frequency, yeah? Let's say the frequency is a constant. And then when the frequency is a constant, I can try, I will consider the momentum space. Let's say kx, ky, and kz. Like this is kz. Yeah. This is kx, and this is a ky. Sorry, ky. And I can plot so-called isofrequency contour. Yeah, isofrequency contour. So isofrequency contour is all possible values of kx, ky, and kz for which omega is a constant. Yeah. And you know that if epsilon ordinary, epsilon extraordinary is 1, this is equation of sphere. Yeah. It is for simplest case. This is just a sphere. Yeah. But if 1 epsilon is negative, it's equation, it's a hyperbola. And let me, it's difficult to plot here, yeah, but it's much easier to show you here, like hyperbolic metamaterials. You see, this is the equation. This is the equation. There are two options, yeah, because ordinary permittivity could be negative, or extraordinary permittivity could be negative, yeah. And there are two cases. And this is another example. So there are two methods for implementation, for realization of hyperbolic metamaterial. The first method we considered, this is like a multilayer structure. You see, like a yellow layer and blue layer, yellow and blue. This is like dielectric metal, like a gold glass. Yeah, this is a so-called type 1 metamaterial with such permittivity. Yeah, but it's also possible to realize hyperbolic metamaterial as a wire medium. Yeah, you have many wires, like metal wires, inside some dielectric. In this case, optical axis is vertical. Yeah, optical axis. For this case, optical axis is horizontal. Yeah, for multilayer structure. Yeah. So it's possible to have ordinary or extraordinary permittivity be negative. Yeah. So in this case, you will have type 1 or type 2 hyperbolic metamaterial. Yeah. I think this is more correct. Yeah. This is like for optical axis vertical, you will have this expression, and this is for wire medium. Yeah. Okay. But why these hyperbolic metamaterials are important? What do you think? Any ideas?
You'd have a propagation constant in some directions.
Yeah. Yes, that is true. There is some forbidden directions. Yeah. But there are two important things. First one, if we consider this classical case, actually, you know, this is the most cited paper of ITMO University. This is a review article about hyperbolic metamaterials. The authors is Alexander Podubny, Vanya Yorsh, Pavel Belov, and Yuri Kevshar. I think this is maybe more than 1,000 citations. So this is the most cited papers for the whole history of ITMO University. But this paper was published just 7 years ago. Yeah. In this published in Nature Photonics. Okay. What is important, guys? What is the difference between this case of a sphere, of ellipsoid or spheroid, and hyperboloid? The main difference is that here all wave numbers are finite. Yeah. So for the fixed frequency, you have a maximal possible wave number. But here, at the same frequency, at fixed frequency, you can have arbitrary large propagation constant. Okay? Arbitrary large propagation constant. So the wavelength can be very, very short. Of course, in this direction, effective medium approximation doesn't work. Yeah. So because if the wave number is huge, wavelength is short, and when the wavelength is comparable with a period, you cannot apply it effective medium approach. You work in a photonic crystal regime. Yeah, but anyway, in an ideal, in a perfect hyperbolic metamaterial, you can have arbitrary high wave numbers. Okay. So it means that you can have very short wavelength at some frequency. It's a way to have some super resolution. And this is some ideas. For example, this is a so-called hyperbolic lens providing some super resolution. Yeah, this is just because of this high K state. So the state of photons with very high wave number. Okay. But the second important thing, what do you know, guys, about density of states? What is the density of states? In Russian, it's плотность состояний. Let me ask you, how many possible states of photon you can have for the fixed energy interval? For the fixed energy interval and frequency interval, it's the same, because energy is just h bar omega. Yeah. How many different states can we have for a photon of fixed energy? What is a quantum numbers of photon in free space? Energy is a quantum number. If you know the energy, you can also calculate what? Free photon is characterized by what?
By frequency.
And it's omega. Frequency is omega. What else? It's not the single characteristics, not the single quantum number for a photon. Wavelengths, but
it's the same.
No, not okay.
Pulse?
Not the wavelength. Frequency, it's an energy. Yes, h omega. But also photon has energy and
spin. No.
It's
impulse.
Yes, spin is kind of polarization, but it's okay. This is true, but polarization, this is true. And what else?
Impulse.
Momentum, exactly. In Russian, it's impulse. But it's a wave number k, because hk is momentum. H bar k, it's momentum, yeah? And momentum is a vector. Momentum has three projections, kx, ky, and kz, yes? And in free space, at fixed frequency, photon can propagate in any direction. Do you agree?
Yes.
With two polarizations. It means that how I can calculate the density of states. The different states is characterized by different projections of momentum on different axes. So the total number of states at fixed frequency is proportional to the total number of different combinations of kx, ky, kz, and polarization. Yeah, because all these states can have the same energy, omega. Okay.
Okay.
So And let me go back to the momentum space. I plot isofrequency surface. Yeah. It means that each point at this surface, each point of this surface corresponds to the some state of photon. Yeah. Each point.
Yes.
So each point has the same energy but different component of wave number. So it means that the total number of states is proportional to the surface area of my isofrequency surface. Total number of states at fixed frequency is proportional to the surface area. In Russian, полное число состояний фотона, то есть с различными компонентами момента или волнового вектора, но при фиксированной частоте, пропорционально площади поверхности изочастотной поверхности. It means that for dielectric, this surface area is a surface area of ellipsoid or sphere, and this surface area is finite. Surface area is finite, but for hyperboloid, surface area is infinite. Yes? Surface area is infinite, and this is the main difference. Surface area is infinite, and this is a slide is just shows you. Yeah. So if you will take some energy interval, yes, you see this is this figure, this one. Yeah. It's like a volume between two neighbor isofrequency surface areas. Yeah. Isofrequency surfaces. Okay. So what can you say, guys, about density of states for hyperbolic metamaterial?
It is infinite.
Exactly. It's a singular. And this is why hyperbolic metamaterials are so important. Because hyperbolic metamaterials are characterized by a singularity in a photon density of states, in photonic density of states. So, for example, if you put some dipole, some oscillating dipole inside hyperbolic metamaterial, what is and probability to radiate energy, to radiate electromagnetic wave is proportional to the density of allowed state. What is radiation? So if you have a dipole, yes, some dipole, and this dipole can radiate some photons in free space. But why this dipole can radiate photons? Because we have in the environment, we have plane waves with such frequency. These waves are not forbidden. Yes? If the dipole oscillates at frequency omega, it can radiate some waves at the same frequency omega. Yeah? So it means that if it's in vacuum, yeah, in this case, all possible states for photons in free space are described by a sphere in momentum space. Yeah. Do you agree, guys?
Yes.
And probability, radiation rate for dipole is proportional to the density of states. But if I put the hyperbolic, the dipole to hyperbolic metamaterial, it will radiate much faster, because for this dipole to radiate photons is much easier because there are a lot of empty states. It can radiate photons at the same frequency at any wave number. And it is why the radiation rate can be very huge inside hyperbolic metamaterial. And this enhancement of radiation, because we change the density of optical states of the environment, is called Purcell effect. In Russian, effect Parcela. And this enhancement is called Purcell factor. In Russian, factor Parcela. Have you heard about the Purcell effect?
Not really.
Not really. It's very famous effects, and in metamaterial community, so a lot of the people discuss about Purcell effect and dielectrics and metals and hyperbolic metamaterials. That's Purcell effect. Purcell effect is enhancement of radiation. So it means that radiation rate of the same dipole depends on the environment. If you put the dipole D, do you remember what is equal to radiated power? Total radiated power by dipole, P. It's 1/3 C cube and omega to 4 and D square. Do you remember, yeah?
Yes.
So, and here you see this omega to 4/C cube. Okay, and actually we can calculate density of states for free space. And we will see that the radiation rate of a point dipole is proportional. We could rewrite this formula in terms of density of optical states in vacuum. And we will see that the radiation rate is proportional to the density of states. So, but if in hyperbolic materials, this is huge. Yeah, but actually, of course, it's limited, it's not infinite, because of the finite size of the dipole, and there is no perfect hyperbolic metamaterials. Yeah, and usually we also have some losses. So it gives some limitations for the radiation rate. But anyway, the enhancement could be huge. And you see, for example, just some multilayer structure and some points here at the top of this metamaterial.
Yes.
This is a light sources like quantum dots or something like this. Because if you would like to enhance the radiation rate, you need just to put your dipoles, your quantum dots inside or near the hyperbolic metamaterial, like here or here. See, like a Purcell effect. You see a lot of figures for enhancement. This is some real experiment. You see quantum dots at the top of hyperbolic metamaterial, and people measure the enhancement in comparison with free space. Or like here, you see some multilayer structure and something at the top. See also the dipole over the hyperbolic metamaterial. So it was very popular, let's say maybe 10 years ago. But now it's there are also many works on hyperbolic metamaterials. Okay. Summary. So we see that we can work. Let me show you. Remember, this is like a dispersion for multilayer structure. Yeah, and this dispersion has band gap. But if we work in this region, in the, let's say, green region, yeah. Here, dispersion like linear, yeah, for certain direction, yeah. And we can describe our multilayer structure here like effective medium, like metamaterial. And we can introduce effective parameters. And effectively, my multilayer structure behaves like a uniaxial crystal. And we found the expressions for the ordinary and extraordinary permittivity. Then here, you see, guys, we have some deviation from linear dispersion, yeah? You see?
Yes.
And this deviation comes due to the fact that our wavelength becomes comparable with the period of my structure. So it means that now our metamaterial doesn't behave as a local material. It behaves, so we need to account some internal structure. I mean, we need to account the finite period of my structure in comparison to the wavelength. So, and this non-locality is also called spatial dispersion or non-local response. So non-locality means that we need to account internal structure, like structure of meta-atoms of the period. So here, when the frequency is very low, we have like a standard metamaterials response, like effective medium approach works. Then when we have a deviation from the local response, we need to account so-called spatial dispersion. Actually, it means that in this case, permittivity epsilon will be a function of wave number. So permittivity depends on kx, ky, and kz. This means a spatial dispersion or non-local response. And if we will decrease the wavelength further, yes, we will have a regime of photonic crystals. Okay, so the same material can behave like a local metamaterial with local response, non-local metamaterial with spatial dispersion, and then if the wavelength becomes shorter, it behaves like a photonic crystal. The same material depending on the wavelength. Actually, it's, you know that let me consider interaction of electromagnetic wave with let's say diamond. Diamond is a crystal, yeah, and for visible wavelength, diamond behaves like an effective medium. Yes, it's like a transparent glass, yeah. But if I increase the frequency of radiation from visible to X-ray, for X-ray radiation, it's also electromagnetic waves, but the wavelength is very short, and the wavelength is comparable with the period of atomic period of my structure. In this case, you will have a diffraction, yes? And this is a kind of regime of photonic crystal. When you have a diffraction of electromagnetic waves on atomic structure of my crystal, it's also kind of photonic crystal, yeah? We could describe interaction of X-rays with their crystalline structure in terms of photonic crystals. Okay, questions, guys? Oh, everything is clear?
Everything is clear.
Okay, everything is clear. So, today we just introduced the effective medium approximation, show that multilayer structure behaves as uniaxial crystal, and also in case of metallic layers, it can behave like a hyperbolic metamaterial. And we introduced the term hyperbolic metamaterial.